Good day, ladies and gentlemen. We are all welcome to Cmen405 Digital Electronics 2 lecture number 4. And this lecture is going to start looking at what we call registers. So what are these registers? These registers, they are nothing but group of binary memory cells for storing binary information, and they are designed to use flip-flops because we have said that the flip-flop is the basic memory element of sequential logic, which has ability of storing 1 bit of digital data. So whenever we want to make n bit register, we have to use n flip-flops because each flip-flop can store a single bit of information. And these flip-flops, sometimes they are designed containing the flip-flops and the logic gates, and the function of logic gates where they are used is to determine the transition of data from one level to another or from one form to another. And of course, the simplest type of registers, they are made using flip-flops only, and these registers, they are used in two categories. The ones that are used for storing data permanently, they are called latch registers, and the registers that are used for holding data temporarily before it is transferred to the final destination, they are called buffer. And a typical example of buffer is in a printer operation. If you send 2 documents to your printer to print, of course it will start printing the first one, and the second one it will keep it in the buffer until when the first one finish, then it will pass it to the printer for printing operation. As we have said, the registers that are simplest in nature, they are the ones that are made using only flip-flops. And here is a typical example of the simplest flip-flop, which is designed using D-type flip-flop. The reason why we said this one is the simplest is the fact that if you can remember, the next equation for D-type flip-flop, Q of T plus 1 is always equal to D, meaning whatever is your input at a particular time should be exactly your output. So this flip-flop register that is designed using D flip-flop is the simplest one, and as you can see here, it has 4 flip-flops, one accepting input I1, I2, I3 and I4, and the corresponding outputs are X1 to X4. Then we come to what we call shift register. As this name implies, they are registers whose content is modified by shifting their content either to the right direction or to the left direction depending on their designs. And these shift registers, they are classified based on how the data is loaded to them and how it is read from them. And based on this fact, we have 4 different types. The first one is called serial in, serial out shift register, and this is the typical block diagram of our shift register, that is serial in and serial out. The reason why it is called serial in is that the information is entering the register bit by bit, and the reason why it is called serial out is the fact that the output is taken bit by bit from the register. And if you look at this one, the fact that it is a shift register is illustrated here because whenever 1 bit comes in, a bit will be going out, so therefore it is shifting, and it depends on how the shifting is taking place. Is it in the right direction or in the left direction? But the most important here is that it is taking inputs serially and it is producing output in a serial manner. Then the second type is called serial in, parallel out shift register, and if you look at this one, the information is going bit by bit, but we can read the content of all the flip-flops at the same time, and that is why we call it parallel out. So the next one, which is number 3, is called parallel in serial out shift register, and as the name implies, the input is delivered all at a time into the register, but we take the output one after the other. As you can see, these are our input going into the register at the same time, but the output are taken bit by bit. That is why we call it parallel in serial out. And the last one, which is number 4, is parallel in serial out, and it is illustrated here. You can see that all the 8 bits are going into the register at the same time, and all the outputs are taking all the 8 at the same time as output. Therefore, they are going in parallel, and they are coming out in parallel. That is why it is called parallel in serial out. So the next thing here is we are going to look at what we call the serial load shift register. And this serial load shift register, what we have seen before is just illustration of the block diagram, but here we are going to see the typical logic diagram. And this serial load shift register, it is designed using the flip-flops, and the reason for this is the fact that it is simplest because the next state equation shown here, Q of t plus 1 is equal to d, meaning whatever is our input at a time should be our corresponding output. And this is an example of 4 bits serial load register. And if you look at this, the input is coming from the post flip-flop, and the output of the post flip-flop is used for driving the next one, while its output is driving the next one up to the last one. And this is the reason why we call it serial load, because we are taking the inputs into it one after the other. And also, as we know, the flip-flops do have, or they need a clock input. That is a signal that will be driving them, and this is our clock that is driving all the 4 flip-flops we have. And at the same time, all the flip-flops, they have a clear terminal that if you want to reset all of them to 0, you apply 0 at this clear terminal. And if you look at this one, at the same time, we know that the data is going in bit by bit, therefore it is serial loads. But if we wish, we can be taking our output only at the external, I mean the last one here, bit by bit, so we can say this is serial in, parallel out. But if you wish, you can, I mean serial out, but if you wish, you can take all the 4 bits output at the same time, so in that case it is serial in, parallel out. And as I have said, whenever the clear signal is equal to 0, all the flip-flops should be reset to 0, 0, 0, 0. And when the clock is applied, it shifts the content to the right. For instance, when we reset it to 0, 0, when you apply this 0, it will go in a serial mode, while the last bit here should go out. So if it goes out, this is what should be the next contents. That is, this one go out, this one move to its place, this one move to its place, and this one move to this place, while this external one occupy the post position, and this is what we have. That is why we are saying that it is shifting in the right direction. This table is a typical illustration of how the content of the serial loads register changes. In the first place, when your clear is equal to 0, all your Qs, that is Q1, Q2, Q3, and Q4, should be reset to zeros, whatever was their previous value. And at that point, the moment the clear is 0, regardless to what is your data, this one should be 0, 0. But when the clear is equal to 1 and your clock is equal to 1, it means your register is now ready to start accepting your data, and this is our corresponding data. It means this one will go and occupy the place of this Q1 as you have seen here, while the last bit should go out. Then when at the next stage our clear is 1 and the clock is 1, and this is our input data, it will enter this place, so that this one will move to the next place, while the last 0 here should go out. When you deliver another 1, it will shift where the last 0 should go out. And if you deliver another 1, if you deliver 1 here now, this 0 should go and replace this 1 here, while this one should move here, this one should move here, and this one should move here. So you can see that it is shifting in the right direction. And if you deliver another 1, what will happen is that this, another 0, this 0 should go and displace this and occupy its place, while this one should move to this place, this one should move to this place, and this one should move to this place. So what we have seen here is that whenever our clear is 0, regardless to what is your data, all the Q's should be 0. But when the clear is 1 and the clock is 1, whatever is your data should take the place of Q1, and the previous Q1 should move to Q2, previous Q2 should move to Q3, previous Q3 should go to Q4, while the Q4 should go out. Now this register, as I have said, if I am to go back to this place, it is a typical example of serial in, parallel out, because we can take all the 4 output, that is Q1, Q2, Q3 at the same time. But if you wish, you can just deliver your input in a serial mode and take output at this terminal point. Therefore it is serial in, serial out at that point. So as I have said, it can be converted to work in serial in and serial out, as I have just illustrated. And of course here we illustrated only 4 bits serial load register, but we can convert it to any number of bits, n bits, if we increase the number of flip-flops we use there. And of course here we have seen how this serial load register is designed using the flip-flops, but at the same time you can use other flip-flops to design it, but it will be a bit complex than this, because their nested equations, they are quite different from that of D flip-flop. Now the next thing is to look at the parallel load register. And the reason why it is called parallel load is the fact that the data is applied to the register in parallel mode, that is all the bits at the same time. And of course we use flip-flops in this case together with the logic gates. As we have said, their function of the gate is to control the inflow of the input data. And this is a typical logic diagram of 3-bit parallel load register. And if you look at it, we have 3 flip-flops, because we are designing 3-bit, and the type of flip-flops we use here, the SR flip-flops. And if you look at it, the S and R for all the 3 flip-flops, they are receiving their input from AND gates, and these AND gates, they are connected to the external sources. One of them from our eyes, that is the external input data, and the other input from our loads. Okay, so if you look at this diagram, it is evident that whenever this load is equal to 0, it means one of the input of this AND gate, this AND gate, this AND gate, this AND gate, all of them, one of their input is 0, because load is connected to all of them. So when one of the inputs of AND gate is equal to 0, automatically the outputs of those AND gates should be 0. So in that case, our S and R for all the flip-flops are 0. And in a situation where the load is equal to 1, so what should determine whether the output of an AND gate should be 1 or not? Depends on this I. When the I is equal to 1 and the load is 1, you can see that what is coming here is the real I, therefore here should be 1. But here we pass it through an inverter, therefore this one should give 0, the same thing to the remaining. So as I have said, whenever our clear in this case also is equal to 0, all the output should be reset to 0. And also if our load is equal to 0, as I have just said, all the one of the inputs of all the 6 AND gates should be 0, which means their output should also be 0s. Therefore in that case my S and R should be equal to 0, and so there is no change in the output. What is the reason? Look at the next state equation for the RS flip-flop. When S is 0, this one becomes 0, and here when R is 0, the prime of R should be 1. 1 times Q should be Q, which means our next output should be the same thing as the previous output. This is what we are saying here. But when the load is equal to 1, then what should determine what happened to S and R is the value of these inputs, that is I1 to I3. Let us take a typical example. When I is equal to 1, when I is equal to 1, our corresponding S should be 1 and the corresponding R should be 0. Let us go back to the logic diagram. If this I1 is equal to 1, automatically what is coming here should be 1, and our load we said is equal to 1, which means the output should be 1, making our S to be 1. And at the same time, when this I is 0, it's inverted through this one. Therefore, one of the input of this AND gate should be 0, the output should be 0, and our corresponding R should be 0. That is what we are trying to explain. So in that case, whenever my load is equal to 1 and my I's have some particular values, the output should depend on the outcome of this next state equation. And this is a typical example of parallel in, parallel out register. Why? Because all our inputs I1, I2 and I3 are delivered at the same time, and all the output Q1, Q2 and Q3 are taken at the same time. Therefore it is parallel in, parallel out. So in this case, we illustrate how it operates. First of all, whenever your clear is equal to 0, so regardless to what is your clock, regardless to what is your load, and regardless to what are your 3 inputs, your output must be equal to 0 for the fact that clear is equal to 0. But when clear is equal to 0 and load is equal to, clear is equal to 1, load is equal to 0, in this case, whatever are the values of your 3 inputs, still the output should remain zeros, because we have seen that whenever the load is equal to 0, my S is 0 and R is 0. Therefore the next output should be the same thing as the previous output, which is these 3 full zeros. But in a situation where the clear is 1 and load is 1, now whatever is my I should determine what should happen. My clear is 1 and load is 1 and clock is 1. Now it is ready to accept your input, and these are my 3 inputs, I1, I2 and I3. So the corresponding output should be 1, 0, 1, just like we have our input 1, 0, 1. And also when clear is 1, clock is 1, data is 1, now it is ready to accept input. And when your inputs I1, I2 and I3 are 0, 1, 0, the same thing, your output should be 0, 1, 0. So the next thing is we are going to look at the universal shift register. This is called universal because it can work as serial load register, and it's at the same time it can work as parallel load register. And of course we can adapt it to work as shift right or shift left register. And this universal shift register, it is designed using or in form of integrated circuit IC, and this is the typical part number 74194. And the IC has 45 gate inside, and it has 16 pins, and it is deep, that is dual inline package. If you look at it, this is the typical block diagram. As I told you, this point we call it notch, and we start counting in anti-clockwise direction. Therefore this is my pin 1 to 8, 9 to 16, and they are all leveled. That is pin 1 is clear, pin 2 is for shift right serial input, pin 3 to pin 6 they are for the parallel input, pin 7 is shift left serial input, pin 8 is my ground, pin 9 and 10 they are my mode selectors S1 and S0, and pin 11 is my clock. From 12 to 15 they are my output, QA, QB up to QD, and my pin 16 is the VCC, which is the voltage supply to the integrated circuit. Now if we want to work as a shift register, shift right register, what we need to do is to make our selector S0 equal to 1 and S1 equal to 0. In that case, it will work as shift right register. And if you look at the drawing here, this is my S0 equal to 1 and my S1 equal to 0. So in that case, I need my clear terminal, I need my clock terminal, and I will use pin 2 because that is the point for shift right serial input, and these are my 4 output as we have illustrated before. Condition for this to happen is that my S0 must be 1 and S1 must be 0. Now if I want to use it as a shift left serial register, these are the values of my selectors. S0 should be 0, S1 should be 1, and in that case we are going to use pin 7 because it is the one for shift left serial inputs. And when I want it to work as a parallel load, in that case my S0 and S1 should be 1 1, all of them. And if you look at it, I then use my 4 terminals for taking the parallel inputs, and this is my clock and this is my clear. And finally, whenever you want to use it in what we call inhibit mode, this inhibit mode simply means to stop it from working at all. If you want that to happen, you have to make sure that your S0 is equal to 0 and your S1 is equal to 0. In that case, it is in inhibit mode and it will never work at all. So this is the end of this lecture. Thank you very much for your attention. I advise you to watch it over and over until you understand. In case you have any problem, don't hesitate to contact me. Thank you very much for now.